Hi folks, Dr. Bruno here. Welcome to Lecture 3. In this lecture, we're going to break the material up into 4 videos. The first video, we're going to cover hypothesis testing. The second video, we're going to cover the difference between one- and two-tailed tests. In the third video, we're going to cover the difference between type 1 and type 2 error. And then finally, we're going to round everything out with a video on power. So let's go ahead and get started. Okay, let's get into hypothesis testing. So when we talk about a hypothesis, typically what we think of is what's known as an educated guess. And my thinking here is that most of your experiences have been on what's known as a substantive hypothesis, right? Which is what you think as a scientific researcher is going to be the outcome or likely outcome for a particular experiment. But in a statistical world, we define a hypothesis as a statement about a population parameter or a sample statistic variable that you expect to be true based on available evidence. So as opposed to just making an educated guess, hypothesis testing when it comes to statistics is all about making a statement about a population parameter that we're trying to generalize about from sample statistics data that we collect. And so we haven't done the experiment yet, but the goal is to collect data with a sample and to extrapolate and generalize that data to the larger population. So when we talk about the process of what's known as hypothesis testing, what we're really referring to is we're comparing a mean value or the average value that we talked about in the central tendency series from a specific group or from people that are experiencing a particular condition, right? And so the goal here is to compare the mean value of an experimental group or an experimental condition to another known population variable, to a different group's mean or average value, or to a different condition value with the same group of people. So the way that it works is we are collecting sample statistics and we're trying to generalize and infer back to a population of interest. And the goal is the data that we collect from the sample, we can generate a mean and a standard deviation from the sample and try to make inferences to the population. We can do it by comparing the mean of the sample to the known population parameter, or the mean of the sample to another comparison group mean and sample. Or if it's in the case of conditions, let's say we're trying to have one group of people experience one condition and then have the same group of people come back and experience a different condition. We can collect mean data under both conditions, and comparing the mean and the standard deviation of the same group of people from one condition can then be done with the same group of people, but under a different condition. So we can compare the mean and standard deviation of both. And that is what hypothesis testing is doing. So a lot of what you're going to learn in this class is what's known as null and alternative hypotheses. And so when we talk about a null hypothesis, we can demonstrate it in a couple of different ways. You can see from the slide that we can represent it as HO, and that's common in most statistic textbooks. And what the null hypothesis is it's a statement that states that there is no difference between your hypothesized group, your experimental group, let's say, and the mean value or the known mean value of a population, or compared to a control group that is not experiencing the experimental condition, or to a placebo that does not have a substance or drug of interest. So the null hypothesis basically means that we don't think it's going to work, right? We expect that when I take data from this sample of people that represent the larger population, that there's going to be no difference between the mean of the experimental sample in the known population or the mean of the experimental sample in a comparison control group mean and standard deviation. So there's not going to be any difference. So when we talk about the null, we mean that there's no difference between the experimental group and the control group, the experimental group and a known population group, or the experimental group condition compared to the control condition. So there's no difference between those two. Alternatively, no pun intended, the alternate hypothesis is a statement that disagrees with the null and states that there will be a statistically significant difference between the experimental group and the control group, the experimental group and the population, or the experimental condition to a control condition. So we'll get into this, but this is a common theme that I'm going to be asking of you to know the difference of with every statistical procedure that we perform this term. So make sure that we review this, okay? So the next thing to think about is what's known as the steps or the order of operations, so to speak, when we are performing what's known as a hypothesis test. And so the first thing that you need to do is you need to determine your alternate hypothesis, or what other people will call your substantive hypothesis, which is, what do you think this experiment is going to do to your dependent variable of interest? Do you think it's going to work better compared to a control condition or better compared to a control group? Do you expect it to perform a little bit worse compared to a control group or to a control condition? You have to make that decision. And so the first thing you need to think about is, what is the alternative hypothesis that you are trying to estimate with doing this study to begin with? And so once you do that, then you need to state your hypothesis as a null hypothesis, right? Which basically states that once you write what you think is going to happen, we're then going to organize it in terms of an HO and an HA, which we talked about in the previous slide. So the HO, remember, is going to state that there is no statistical difference between mean 1 and mean 2, and mean 1 can represent experiment 1 and experiment 2, or experiment versus control, or experiment versus population. These are all different ways. We're just comparing the experimental condition to some other mean and standard deviation. Could be in the same group, could be different people. We'll go through all those examples this term. So once you have the null, then you can write the alternate, which is the alternate to the null, which states that there will be a difference, or there will be a relationship between the experimental conditions mean and standard deviation and a control, the population, etc. We've been over that a few times now. So once you do that and you get your substantive hypothesis of what you think is going to happen, and then you structure your statistical hypotheses in terms of null and alternative hypotheses, the next thing you need to do is you need to organize the data using some of the techniques we talked about in previous videos, and you need to perform a statistical analysis to ultimately determine if you should reject the alternate hypothesis, which means that you will accept the alternate hypothesis, or if you choose to accept the null hypothesis and reject the alternate hypothesis. So really what you have to do is you have to run a statistical analysis to see if there's a statistically significant difference between the means. And if there's no difference between the means, well, then that supports the null, which said that there's no difference. If there is a difference between the mean, well, then you'll reject the null and accept the alternate, because the alternate is what's true. So that's how we go about deciding upon rejecting and accepting the null hypothesis. So here's a nice example that I like to use in the class. So let's say that we have a data set, and a statistical analysis can compare the mean blood glucose values between a healthy group of people, right? Those are your control people, versus a diabetic group. So let's say we have a population of interest, which is people that live with type 2 diabetes. And one of the things that rules a person in for diabetes is high blood glucose concentrations. So if I wanted to run a statistical analysis and I wanted to compare the average or the mean blood glucose values for a group of people that were healthy and otherwise free of type 2 diabetes, and I wanted to compare the means and the standard deviations of blood glucose values to a group of people who had known diabetes, we can ultimately look at the dependent variable in this case, which would be fasting blood glucose, and we can use a glucometer, as you see here on the slide, to get a sample of each person's blood and to assess the concentration of blood glucose in the sample. So the alternate hypothesis to this experiment would state that the blood glucose levels that are collected from the glucometer, the mean and the standard deviation of the blood glucose for the experimental group, which would be the diabetics, is not statistically different from the mean and the standard deviation of the control group, the non-diabetics or the healthy group of people. The alternate hypothesis, therefore, would state that the blood glucose concentration between diabetics and healthy participants is statistically different, but it's not determining which has the higher blood glucose concentration. Based off of experience and logic, we may think that the people that live with diabetes will have the higher blood glucose concentrations because that's what literature and experience and evidence has provided to us at this point in time. But we shouldn't make that assumption without first doing the statistics and collecting the data. Okay, that's a very important thing. So then you generate your null hypothesis, which says there's no difference, and then you do the alternate hypothesis, which declares that there is difference. And so you have to write two alternate hypotheses. One is that it's different and the blood glucose concentration will be higher among diabetics compared to healthy populations. And the opposite will be they're going to be different and healthy populations will have higher fasting blood glucose concentrations compared to diabetics. You have to be able to go both ways because until you do the experiment, you don't actually know which of the two is going to have a higher fasting glucose, even though we have a good sense and idea of what it will be. Okay, so then the next thing to think about once we go through this process is we want to talk a little bit about rejecting the null hypothesis or accepting the null hypothesis. So we got a lot of information on this slide. So if you're going to reject or accept the null hypothesis, our goal here is to determine if there is a statistically significant difference between the means, period. If there is, then we reject the null and accept the alternate. If they're the same, then we accept the null and we reject the alternate. So another thing that we need to think about that will go back and forth between this slide and then the subsequent slide next is understanding something that's known as the critical region or the area of rejection. How do we know if there is a statistically significant difference between the means? And we're going to connect it, and I'll teach you how the skill set of how you know that you have significance based off of something that we've learned already this term, which is the normal distribution. So you're going to have an area of acceptance, you're going to have an area of rejection, and we're going to introduce something that's known as a critical value, which is effectively the goal line. So if you think about it in soccer, there's a goal line, or in football, there's a goal line, right? There has to be some level of boundary where if the value exceeds the boundary, it's significant. And if it doesn't exceed the boundary, it doesn't cross the threshold for significance. So just how when a soccer ball doesn't cross the goal line, it's not a goal. And when it does cross the goal line, it is a goal. In a similar way, the goal line, the boundary, the critical value, the value that we calculate has to exceed the critical value. And when it does, then we can declare some significance. So I'll walk you through what that looks like. And then the last thing to think about before we show you what this looks like graphically is what's known as a significance level. And so this has to be determined before you run your statistical analysis. And so we represent significance based off of the Greek notation of alpha. And we say it's alpha equals p less than 0.05, or alpha p less than 0.01, or alpha p less than 0.001. And what this represents, the p in the alpha, represents the probability that the average value you collected from the data falls within that critical region, so past the goal line. And what is the likelihood of that event happening? And when the null hypothesis is true, you should accept the null hypothesis because the value of the mean has not exceeded the critical value that is determined to reject the null and accept the alternate, which again tells us that there's a statistically significant difference in the sample. So once we go through this process, a couple of ways that we have to do this is we have to understand that we use this thing called the normal distribution. And so when we use the normal distribution, we never represent the data in terms of the actual units that we measured. So for example, if we were sticking with that fasting blood glucose value between diabetics and non-diabetics, we wouldn't necessarily state that the mean of one group is going to be the mean, median, mode going down the symmetrical normal distribution. Because remember our characteristics. Has to be bell-shaped, has to be asymptotic, has to be continuous, and has to be symmetrical, right? So symmetrical, bell-shaped, continuous, asymptotic. And we said that the mean median mode in a standardized distribution is always going to be 0, as you see here. So we can't just take data that we collect from diabetics and non-diabetics. We have to be able to convert them into what's known as a z-score. And the way in which we calculate a z-score is you take the value x minus the mean, right? So this is effectively deviance when we're calculating standard deviation. Any particular x score, so this is a person's blood glucose, minus the average blood glucose divided by the standard deviation of the sample's blood glucose. And so when we do that, we're going to get a value that's going to be above or below 3 standard deviations. And so remember, if the mean median mode in a standardized distribution is 0, 68% of the scores is going to fall within 1 standard deviation above and 1 standard deviation below the mean. 95% of scores are going to fall within plus or minus 2 standard deviations above and below the mean. And if they are larger than 3 standard deviations above and below the mean, they would be 99.7% above or below the mean. So very, very low likelihood that that value, should it occur, would fall in that area of rejection. So the way in which we do this is when we calculate the z-score for a particular group, we can pair it and place it onto this normal distribution. And so if the group has a mean score that is larger than 1.96 positive, that tells me that the value is falling in this shaded region of rejection, which, as we know from having a 1-2 standard deviation above the mean, that the likelihood of that happening is only 0.025, or a 2.5% chance of that value falling in that region. So it's not very likely compared to where other scores fall in the distribution. Similarly, if the value for the z-score falls and is negative 1.96, that would mean that it's 2 standard deviations below the mean and would fall once again into an area of shaded region here. So very unlikely, and a 2.5% chance of that happening. So when we go back a couple of slides and we talked about this thing called a critical value, the most common critical value that we're talking about is this plus or minus 1.96. That number is of significance because the significance level predetermined for the alpha is representing the probability that the value, or that the z-score, falls at or at a more extreme value than the critical point. So the likelihood of a z-score falling at 1.96 or more extreme than 1.96, positive or negative, has a very, very low probability of less than a 2.5% chance above and below the mean, which we determined from the alpha level, which was p less than 0.05. So in this particular case, you have a two-tailed alpha, which we'll get to in the next video. And the two-tailed alpha basically says that the alpha is going to be less than p less than 0.05, which means the p, the probability that a z-score value will fall at or at a more extreme value than 1.96, the critical value, is going to be 5% of the time or less. But I have to decide if I want to put that all in one tail to the right or in all in one tail to the left. So what a lot of researchers would do, is in the case here, is they take that 5% and they divide it by 2, and they put 2.5% in one tail, 2.5% in the other tail, for a total of 2.5% in each case. So the likelihood of a value falling at or a more extreme value than 1.96 is actually not very probable at all. So if it is, it means you reject the null hypothesis, you accept the alternate hypothesis, and it's very likely that your experiment worked and caused a difference in that mean value between the mean in the population, the mean in another group, or the mean in another condition. So I hope that was helpful. In the next video, we're going to talk a little bit about one versus two tail tests. We'll see you there.